Okay, so let's now turn to problem set 2, which has 8 questions, and that is a problem set about a game that does not have a solution in pure strategies. We have two players, the government and the terrorist. The government can either go north or south, and the terrorist can also go north or south. Let's first play the game in pure strategies and show that the game has no solution in pure strategies. So if the government thinks that the terrorist goes north, shall the government go north or south? So we compare the 2 to the 1. 2 is better than 1, so we underscore the 2. If the government thinks that the terrorist goes south, shall the government go north or south? So now we compare the 1 to the 4, and of course the 4 is better than the 1, so we underscore the 4 for south. Now let's play the same game for the terrorist. If the terrorist thinks that the government goes north, shall the terrorist then go north and get 3, or go south and get 5? Well, 5 is better than 3, so we underscore the 5. And if the terrorist thinks that the government goes south, shall the terrorist go north and get 4, or south and get 2? Well, 4 is better than 2. We underscore the 4. So you can see the game has no equilibrium in pure strategies. There is not a single cell where both payoffs are underscored. So which statement is true about the game? The government catches a terrorist in the north. No, that would be an equilibrium. Government catches the terrorist in the south. No. So A and B suggest that there is an equilibrium. North is dominant for government, south is dominant for the terrorist. And that also doesn't seem right because no one has a dominant strategy. So this game has no solution, and maybe I should say the game has no solution in pure strategies. Because you can always find a solution in mixed strategies. Okay, so let's call that the game has no solution in pure strategies. Okay, so now in a mixed strategies Nash equilibrium, the government needs to play north with what probability? Okay, so now we focus on the government. The government wants to make sure that when the terrorist goes north or goes south, that the terrorist has the same expected payoff. And that is something that the government can steer by choosing the optimum strategy. So in this case, the government needs to make sure that when the terrorist goes north, that the terrorist gets the 3 with probability P, which the government chooses, plus 4 with the probability 1 minus P. So that is now the expected payoff for the terrorist when the terrorist goes north, depending on the probabilities with which the government goes to the north and the south. And that needs to be equal to the expected payoff when the terrorist goes south. So now, of course, we play a mixed game, a mixed strategy game, which means the game is played over and over again, and we are concerned with the expected payoff. So now the expected payoff for going south is 5 times the probability of P plus 2 with the probability 1 minus P. Okay, so now we need to solve for P. So we get 3P plus 4 minus 4P equals 5P plus 2 minus 2P. So now we can collect terms. 3p minus 4p, we have here negative 1p. We have still the 4 left. Needs to be equal 5p minus 2p, that's 3p. And here we still have a 2. So now we can collect terms. Let's add on both sides 1p. And let's also flip the sides. So then we get 4p, but I put it now on the left side. And we need to subtract 2 on both sides. So then we get here a 2. Then we divide by 4, and then we get the optimum p, which is 2 over 4, or 0.5. So that would be the solution, which is also one of the answers, so we can have some confidence that this is correct. So now we know that the optimum strategy is to play north with a probability of 0.5. So this is p equals 0.5, and then one minus p is of course then also 0.5. In a mixed strategies Nash equilibrium, the government needs to play south. Well, that is also 0.5. In a mixed strategies Nash equilibrium, the terrorist needs to play north with, okay, so now we have to do the same thing for the terrorist. The terrorist wants to make sure that they choose the probability of going to the north and south such that the government has the same expected payoff in going to the north and the south. So that means the terrorist needs to solve the equation 2 times the probability of Q, because the government gets a 2, when the government goes north, it gets a payoff of 2 with the probability of Q when the terrorist goes north, plus 1 time 1 minus Q. So that is the expected payoff for the government when the government goes north, depending on the probabilities with which the terrorist chooses to go north and south. And that needs to be equal to the expected payoff of the government when going south. So that is then 1 times Q plus 4 times 1 minus Q. Okay, so now we got to solve for Q. So we get 2Q plus 1 minus 1Q equals 1Q plus 4 minus 4Q. So now we can collect terms. So we are left on the left side with 1Q plus 1 equals that is plus 4 minus 4Q. 1Q plus 4 minus 4Q. So 1Q minus 4Q, that's negative 3Q plus 4. Okay, so now we can collect terms again. Let's do 4Q. Let's add on both sides 3Q, then we get to the left 4Q. And then let's subtract on both sides 1, and we get 4Q equals 3. So the optimum strategy for Q is 3 over 4, or 0.75. So the best strategy is to go to the north with probability 0.75. course going to the south with probability 0.25. Okay, in a mixed strategies Nash equilibrium, the terrorist needs to play north with probability 0.75. In a mixed strategies Nash equilibrium, the government needs to play south with 0.25. In a mixed strategies Nash equilibrium, the government's expected payoff is. Okay, so now we need to calculate the expected payoffs. And of course they need to be the same. So the government's expected payoff is, when going north, just call it N. So now the government gets 2 with a probability of 0.75. So 2 times 0.75, that's 1.5. Plus gets 1 with the probability of 0.25, so that's 0.25. So that is 1.75. Oops, sorry. And now we can do the same for, so that was the government, let's put here still a G, and now we do the expected payoff for the government when it goes south. So then it gets 1 with a probability of 0.75, 1 times 0.75 is 0.75. And it gets 4 with a probability of 0.25. 4 times 0.25 is 1. So we always get 1.75. And of course that must be the case for the optimum strategy. So that's 1.75. And let's also do the expected payoff for the terrorist when next terrorist goes north. So when the terrorist goes north, it gets 3 with a probability of 0.5. So 3 times 0.5, that's 1.5. And gets 4 with a probability of 0.5. So that's 2. So the expected payoff for the terrorist is 3.5. And if the expected payoff for the terrorist when they go south, probability of 0.25 gets 5 with a probability of 0.5, so that's 2.5 plus probability of 2 with 1. 2 times 0.5 is 1, so that's also 3.5. So the expected payoffs, of course, for the players don't have to be the same. The expected payoffs have to be the same for each player when they play each available strategy. So in the mixed strategies Nash equilibrium, the government's payoff was 1.75. And the terrorist's expected payoff is 3.5. Okay, so now, last question. Now assume that the terrorist plays south with probability 0.75. Then which statement is true? Okay, so basically what happens is, so now we assume that the terrorist does not pursue the optimum strategies. So instead of playing 0.75 north, plays it only with 0.25, but goes to the north with 7.5. So let's highlight that. that this is a special case now. Make it, I don't think that's a good color contrast. Okay, so I highlighted that in green to underscore that these are not the optimum strategies. So now the point here is to see how that changes the expected payoffs. So that will affect, if the terrorist doesn't play the optimum strategies, that will affect the expected payoff of the government. So now we can see how that affects the payoff of the government, and we can see when the terrorist played the optimum mix of strategies, the government could expect 1.75 and 1.75. So I can erase this one here for the terrorist, because now we need to look at the expected payoff for the government when the terrorist does not play the optimum strategy. So I called it expected payoff, government, given, that vertical bar means given, terrorist not play optimum strategy. Okay, so now what does that mean? So now the expected payoff of the government, well, they still get 1.5, so this is still the same. It's actually, no, sorry, no, I forgot to write the probabilities. So then it still gets 2. So if the government goes north, now it gets 2 with a probability of 0.25, so that is 0.5. And I should, that's the expected payoff of the government when going north. So now instead of getting 2 with a probability of 0.75, which gave us the 1.5, the government gets now 2 with a probability of 0.25, so that's 0.5. And the government gets 1 now with a probability of 0.75, so that's 0.75. So that means the expected payoff now for the government to go north has dropped from 1.75 to 1.25. Okay, now what's the expected payoff if the government goes south? So now the government can expect a 1 with probability of 0.25, so that's 0.25, plus 4 with a probability of 0.75. So that is 4 times 3 over 4, so that is 3. Because 4 times 0.75, that's 3, so that's 3.25. So that means when the terrorist does not play their strategies optimally, the government is now always better off to just look in the south, because there the government gets the higher payoff. So the result will be that the government will now always look for the terrorist in the south, because the terrorist doesn't play their strategies optimally. So that when in other words, when the terrorist doesn't choose their strategies in an optimal mix, that favors then the government. So assume that the terrorist plays south with probability 1 minus q equals 0.75. Then which statement is true? Well, this would not be the terrorist's best mixing of strategies. the government should then be best off to only play south and get an expected payoff of 3.25. Well, that is what we just derived, and that is correct. Okay, so I hope that this problem set illustrated or made clear what optimum strategies are and what happens if players don't play the optimum strategies.